All right, this one should be really quick. It's just one of the fundamental problems from chapter 2, looking at normal strain. These problems are really nice. We're just kind of using some basic geometry, maybe some basic trig, more so just like the small angle stuff, and our understanding of what normal strain is. Normal strain is just looking at when we kind of apply, as you can see from this picture, just using this, we apply a load in this direction, we'll get elongation going here, and it's just looking at the difference um, in the length that changes. And you can think of normal as in, your axial normal loading that you get, where, shear is going along. All right, so let's work on this problem. It should be pretty quick. Do purple. All right. When force P is applied to the rigid arm ABC, which we have along here, point B displaces vertically downward through a distance of 0.2 millimeters. All right. So that is our little elongation, which is just the difference in the original and final lengths. And it gives that to us at 0.2 millimeters. Determine the normal strain in wire CD, this guy right here. And normal strain is this epsilon symbol. It'll be equal to that elongation in the member CD, or more so just like the difference in points in C um, over the original distance LO, where LO is equal to 300 millimeters. So we're looking at, if we're going to visualize it, we're looking at, we know that this B will go down a certain way. So if we could draw our little, it's obviously very exaggerated. We're saying that this distance right here for B is that 0.2. It's 2. And we want to look at this distance that C changes. That would be, there we go. All right, and so this we're just going to use that small angle theorem that I think was talked about in your lecture, and kind of just like triangles. So as you can see, this angle right here will be the same, and using that small angle triangle, the ratio is 0.2 over 400 millimeters should be equal to the elongation at C, that difference in length over 600. And then we solve for that, and we get 0.3, which makes sense. It's a little more of a displacement than we see at B. And now we just plug that into this equation and solve for our normal strain. And this time we're using the original length of 300 millimeters, sorry. And we'll get 0.001. And it's actually unitless because it's millimeters over millimeters, which you just cancel out.